Welcome back to chemistry. We're in section 12.3, limiting reactants. Let's begin. At a school dance, the music begins and boys and girls pair up to dance. There are more boys than girls. Some boys will be left without partners. The same is true of reactants in a chemical reaction. Rarely in nature are reactants in a chemical reaction present in the exact ratio specified by the balanced equation. Generally, one or more reactants are in excess, and the reaction proceeds until all of one reactant is used up. Does that make sense? Generally, one or more reactants are in excess, and the reaction proceeds until all of one reactant is used up. So typically what happens, like let's say you're trying to burn something, right? Let's say you're going to try to burn a piece of wood. If you try to burn a piece of wood, you're mixing all the wood molecules with all of the oxygen molecules. Which one will run out first? The wood molecules or the oxygen molecules? That'll be the wood, right? Because you're burning the wood and the wood's just sitting there. Once the wood is burned up, you're done, right? But the oxygen's not going to run out because you have all of the oxygen in the atmosphere to use. So, oh my gosh, Coco, please stop interrupting my class. She proceeds to knock over a shovel in response to me scolding her. That's my dog, everybody. Okay. So yeah, if you're burning a piece of wood, the wood will run out before the oxygen will. Let's look at an example not involving chemistry. Let's say you have this many tools, and I tell you, Cameron, you have 10 screwdrivers, 5 pliers, or bolt cutters. I can't tell with this bad quality. They are pliers, okay. So you have 10 screwdrivers, 5 pliers, and 4 hammers. In order to make a set of tools, I need 2 screwdrivers, 1 set of pliers, and 1 hammer. So Cameron gets on his way and he starts making his sets of tools. He makes 1, 2, 3, 4, and he's on the 5th one, but he notices he doesn't have enough hammers to make a 5th tool. Right? He had enough to make this. He even has enough screwdrivers and pliers to make a 5th tool set, but he does not have enough hammers to make a 5th tool set. Therefore, in this case, the hammer would be a limiting reactant in making these tool sets. He can only make as many tool sets as there are hammers. It doesn't matter if we had a whole truckload of screwdrivers, we can only make 4 sets of tools because we only have 4 of these hammers. Now there's a saying, I think there's a saying that says don't reinvent the wheel. Maybe I'm just mixing statements up, I don't know. But in this video, on the description, there's 3 other videos I'm going to post. And I'm almost done teaching this lesson because there's no point in me redoing these because these 3 videos are going to be exactly what I would do, just with colors and a little more spaced out, a little more time, a little higher production quality because they knew how to do this online stuff and they were prepared for that, and I'm kind of not. So pause this video and go watch those 3 videos. And I know it's kind of a lot, so remember this is for an entire week's worth of information. Pause this video and go watch those before finishing this one. Okay, this is seriously, this is assuming you watched those 3 videos. At the very least, this is assuming you watched that first one, because he goes through starting from the book expects you to remember a lot, and it just kind of dunks you in, but those 3 videos kind of ease you back into where we are right now. So we're going to determine the limiting reactant in one of these problems. And this will be similar to the 3rd video that he showed, that he explained stuff. So the reaction between solid white phosphorus and oxygen produces solid tetraphosphorus decoxide. Question A says determine the mass of tetraphosphorus decoxide formed if 25 grams of phosphorus and 50 grams of oxygen are combined. Question B says how much of the excess reactant remains after the reaction stops. So we know one of these is going to run out before the other one, probably. And our question is, letter B says, how much of the extra will we have? And question A says, how much of the product do we get? So we know what the reactants are. How much of the product do we get if we have this stuff? Okay? And white phosphorus is crazy flammable. You can't actually find it like in the real world because it just starts lighting everything on fire, so you won't find it. Does that make sense? Like if it's in the wild, it already combined with something else because it can't exist as this white phosphorus. It'll just burn. So you're given the masses of both the reactants. So the limiting reactant must be identified and used for finding the mass of the product. From moles of the limiting reactant, the moles of the excess reactant used in the reaction can be determined. The number of moles of excess reactant that actually reacted can be converted to mass and subtracted from the given mass to find the amount in excess. So this is essentially what we're trying to do. If we find the moles of both of these, we can find out how many moles of our answer we got, which means we can easily convert moles of this to grams of this. And if we find out how many moles are left over of this excess reactant, then we can find out how many grams are left over. So we're going to be using molar ratios and a bunch of molar mass conversion factors in order to do this problem. So first up, let's write the balanced chemical equation. Now, the way the problem is written, you don't actually know the balanced chemical equation. It says there's phosphorus, there's oxygen, and it makes tetraphosphorus dicoxide. You have to go and balance it. It does tell you what P4 looks like, and it does tell you what O2 looks like, and it does tell you what P4O10 looks like, but it does not tell you that there's a 5 here. Hopefully you guys can see that we put the 5 here to have 10 oxygen molecules, so we can get P4O10 over there, and everything is balanced. My dog is currently trying to throw a broom outside my window. Okay. So first, let's go from grams to moles, because if we get it to moles, then we can do molar ratios, right? And that's what the lesson 1 and 2 were about. So we start with 25 grams of P4. Let's convert that to moles. Well, how do we do that? Remember, since this is grams, we want to put the grams on the bottom. And this is the molar mass of P4. And we find this by just multiplying 4 times the molar mass of 1 phosphorus, and we get 123.9. So 25 divided by 123.9 gets us 0.202. Let's convert the number of moles of oxygen. I'm sorry, let's go from grams of oxygen to moles of oxygen. We have 50. We put 1 mole of O2 over 32 grams of O2. We're getting 32 because 16 times 2 is 32. So 50 divided by 32 is 1.56. At this point, the way the book solves the problem is different than the way the videos solve the problem, but both are 100% correct, which is why I wanted to do one from the book. So let's calculate the actual ratio of available moles of O2 and available moles of P4, which means we're going to look at what we have, and we're going to compare those ratios to what the problem says that we should have, what the balanced chemical equation says we should have. So what we can do here is say, let's put moles of oxygen on top of moles of phosphorus. Moles of oxygen on top of moles of phosphorus. Okay? So if we divide 1.56 by 0.202, you put that in your calculator, you will get 7.72, which means this is the same thing as writing 7.72 on top of 1. Do you guys see that? This fraction is the same as this fraction. It might not feel like it looks the same, but it is. These two are the equivalent fractions. They're the same thing. Notice the units stay where they were, but the numbers seemingly changed for no reason. But that's because if you put these two numbers in your calculator, you get 7.72. Well, 7.72 over 1 is just 7.72, so we can write it like this, and it still counts. Okay, so this is what the actual stuff we have, right? We had 25 grams of phosphorus, 50 grams of oxygen. What does it have to do with moles? Well, if we convert all that stuff to moles, that means we have 7.72 moles of O2 for every 1 mole of phosphorus. Okay, so we have 1.56 moles of O2 for every 0.202 moles of P4. And then I said all we have to do is divide that by that, and we get 7.72. 7.72 divided by 1 is the same thing as this. Okay, so now we're going to compare our problem with our balanced chemical equation. So that's what I'm doing here. This is the actual stuff that we have based off of our 25 grams and our 50 grams. This is based off of the math we just did. 7.72 moles of O2 for every 1 mole of P4. Our balanced chemical equation says to do this correctly, we only need 5 moles of O2 for every 1 mole of P4. Okay, 7.72 to 1, 5 to 1. 7.72 to 1, 5 to 1. Okay, so what this tells us is that we have extra oxygen, right? If we didn't, then this number should be 5. Since this number is bigger than 5, we have more oxygen than the problem needs. Does that make sense? This number is bigger than that one, so we have more oxygen than this problem needs. So that's why I wrote down here, we have extra O2. We have more oxygen than the problem needs, so P4 is a limiting reactant. Knowing that P4 is a limiting reactant lets us know which thing to focus on, which is P4, to find out how much of the product we get. Okay, so P4 is the thing we should focus on because that's our limiting reactant. So let's look at this again. If we had 0.202 moles of P4, and our question A says, how much of our product do we get? Well, we need to use a molar ratio comparing P4 to tetraphosphorus dicoxide. Well, looking at our balanced chemical equation, for every 1 mole of P4 I have, how many moles of P4O10 do I have? Hopefully you guys realize it's just 1 to 1 because there's an invisible 1 here and an invisible 1 there, right? So if I have 0.202 moles of P4, how many moles of P4O10 do I make? Let's use the molar ratio we just found, which is just 1 mole divided by 1 mole, which is just 1, which means for every 0.202 moles of P4, I have 0.202 moles of P4O10 being made. And remember, the reason why we're not using oxygen for this is because we have too much oxygen. Oxygen is in excess. We essentially don't have to worry about that. Okay? 0.202 moles. Now let's convert that to mass because the question asks for mass. So 0.202 moles of P4O10 multiplied by its molar mass will get us 57.3. At that point, we are done with question A. A said, how much of our product do we have? 57.3 grams. Question B said, though, what's the mass of our excess reactant? Well, we already found out that O2 was our excess reactant. So that means, excuse me, that means only part of it, only part of the oxygen is being used. There's going to be extra left over. So we're still concerned with how much we're using based off of P4 because P4 is our limiting reactant. It's the thing that determines the rest of the problems. So if 0.202 moles of P4 is used, how many moles of O2 are used? Okay, well, that is pretty straightforward because we know in our problem we need to use our molar ratio. So for every one of these, how many of these do I need? Hopefully you guys can see that answer is 5. For every one of these, I need 5 of these. So we use that right here. For every 1 mole of phosphorus, I have 5 moles of oxygen. So I can cancel those out. 0.202 times 5 means 1.01 moles. That's all of the oxygen I need. That's all I need. Okay? So let's find out how much I need, subtract that from how much we had, and then we can find out how much we have left. So let's find out how much we need. 1 mole, 1.01 mole of oxygen multiplied by its molar mass gets us 32.3 grams needed. That's the mass of oxygen we need. Subtract that from how much we started out with, and that gets us 17.7 grams. That's how much excess oxygen we have. So we have a bunch of extra oxygen. And that's about it. Again, if you got this far without watching those other 3 videos, I heavily encourage you to watch those other 3 videos before starting any of your homework. Otherwise, that's about it.